In this video, we'll see how we can use the horseshoe to represent another series of expressions, such as only if or unless, as well as to state necessary and sufficient conditions. In this video in particular, we're going to talk about only if and necessary and sufficient conditions. We'll deal with unless in our next video. Here we have examples of sentences that can be represented with the conditional of propositional logic, that is the horseshoe. And so we have sentences containing if, only if, unless, is a sufficient condition, is a necessary condition, and I've included here if and only if, and necessary and sufficient condition, because you can perfectly well represent them with a conditional, though usually they are more concisely represented with the biconditional, which is a connective that we'll introduce later on. In order to know how to symbolize a given expression in propositional logic, we use a truth table. We're going to do that with only if. An example of a sentence is, you will join the club only if you become friends with Al. The two components are the sentences, you join the club and you become friends with Al. Let's see what happens to the whole sentence depending on the truth values of the component sentences. Let's begin with the first row. Here there's no reason to think that the sentence is false, so let's make it true. Now the second row, in this row, you join the club is true, but you become friends with Al is false. This means that you can join the club without becoming friends with Al. And so the condition expressed by you will join the club only if you become friends with Al is false. And in fact, this is the only situation in which the sentence comes out false. For instance, let's go to the fourth row, in which you don't become friends with Al and you don't join the club. This is in consonance with the rule which says that the only way to join the club is to become friends with Al. So we make it true. Row 3 is the trickiest one. This is the case in which you become friends with Al, but you don't join the club. It might seem, on first impressions, that this makes the whole sentence false, but it doesn't. Notice that what the sentence says is that if you don't become friends with Al, you won't join the club. It doesn't say that by becoming friends with Al, you automatically get club membership. Perhaps you happen to like Al, but have no interest in becoming a club member. Or perhaps becoming friends with Al is not the only condition. Perhaps you also have to become friends with Sally to become membership, so that if you fail to become friends with either Al or Sally, then there is no chance of becoming a member of the club. This applies in general to sentences of the form P only if Q. They are only false when P is true and Q is false, and are true otherwise. And this makes sense, given that Q is supposedly giving you the condition without which P cannot be true, so that if P is true without Q also being true, then it is not the case that P only if Q. Now let's look at the same truth table again, the one that we made for P only if Q. Well, it happens to be identical to that of a connective we've already studied. Do you know which one it is? Think about it for a second. The truth table is identical to that of the horseshoe. So P only if Q is, in propositional logic, equivalent to if P then Q, meaning that whenever one of those sentences is true, the other one is true as well. And whenever one is false, the other one is also false. So they are logically equivalent because they always have the same truth value. And so they can be used indistinctly to represent the same sentences. Also, notice that if P then Q is also equivalent to if not Q, then not P. This can be seen in this truth table, where we have a column for if P then Q and one for if not Q, then not P, side by side. And again, we see that no matter which case we consider, they always have the same truth value. This means that they are equivalent. In consequence, we can see that there are two equivalent ways of expressing P only if Q. And those are if P then Q and if not Q, then not P. Talk of necessary conditions and sufficient conditions can also be represented by means of the propositional logic conditional. When we say that P is a sufficient condition for Q, what we mean is that if P obtains, then automatically Q obtains as well. On the other hand, when we say that P is a necessary condition for Q, what we're saying is that if P doesn't obtain, Q doesn't obtain either. So let's test our understanding of these notions. Let's begin with A. Is being single a sufficient condition or a necessary condition for being a bachelor? Well, it's clearly not a sufficient condition because you can be single without being a bachelor. Suppose that you're a female, for instance. However, it is a necessary condition for being a bachelor because nobody who isn't single can be a bachelor. We can see the opposite with B. Having been born in Salt Lake City is a sufficient condition for being a Utah, because by being born in Salt Lake City, you automatically qualify as having been born in Utah. However, it's not a necessary condition because you can be born in Utah without having been born in Salt Lake. You might have been born in Provo, for instance. So, which of these truth tables corresponds to P is a sufficient condition for Q? To make it more concrete, suppose that P is you bribe Al and Q is you get your diploma. Let's focus on the rows in which we get false. In the first table, it is the second row, and in the second table, it is the third row. Saying that bribing Al is a sufficient condition for getting your diploma is the same as saying that by bribing Al, you automatically get the diploma. And what is ruled out is that you bribe Al but don't get the diploma. So it should be false in the case where P is true and Q is false. And that is what happens in the second row. But notice that the table we end up with is the same as the one for the conditional. So we can see that P is a sufficient condition for Q is equivalent to if P, then Q. The other table corresponds to P is a necessary condition for Q. Suppose that P stands for you befriend Al, and Q stands for you join the club. So befriending Al, that is P, is a necessary condition for joining the club, is false if you can join the club without befriending Al. So the case in which this sentence is false is that in which you join the club but do not befriend Al. That is the case in which Q is true but P is false, which is precisely what you obtain here. So P is a necessary condition for Q is equivalent to if Q then P. Now, as this table shows, if Q then P is equivalent to if not P then not Q. So this gives us another way of expressing P is a necessary condition for Q. Okay, this is all for now.